Part 3. Sound Propagation.
Everyone knows that the level of a sound decreases as we increase the distance from the source. What we want to look at is, to what extent does it change? How much is the sound level decreased in quantitative terms, and to what extent is the frequency changed? The factors influencing these changes that we're going to look at are, first, distance, secondly, the type of source, third, the intervening atmosphere, and fourth, intervening objects. The simplest and most common case when we're looking at the effect of distance on sound level is that of a point source in a free field. Point source is simply a small source. Mathematically, it's a point, but in reality, it's all relative to distance. If we get far enough away, everything becomes a point. The free field simply means that there are no intervening buildings, walls, objects to reflect sound back. And so this would be the case very often outdoors, at least for certain distances. In this idealized case, the power loss is proportional to the distance squared. In other words, we have the inverse square law applying here. The change in the sound pressure level, therefore, will be 10 times the logarithm of the ratio of the distances, d1 over d2 squared. And using one of our logarithm rules, we can pull that squared factor out to the front, and we find that the change in sound pressure level is 20 times the log of d1 over d2. So if you look at the table on the right there, if the d1 over d2 is 2, then the change in sound pressure level is 6. If it's 4, the change is 12. If it's 8, the change is 18. If the change is 10 times the distance, then the change in sound pressure level is 20. And for 100 times the distance factor, the change in sound pressure level is 40. One can always do the math to determine the change in sound pressure level going from any one distance to any other distance. Very often we express this as a simple rule of thumb, which is 6 decibels for every doubling of distance. So if d1 over d2 is 2, or 1/2, either way we look at it, then 20 times the logarithm of 2 is 20 times 0.3, or 6 decibels. Just a simple way to remember that approximately 6 decibel change will take place every time we change the distance by a factor of 2. And of course, if we're increasing the distance, the change in sound pressure level is going to be a minus 6 decibels. If we're decreasing the distance, the change in sound pressure level will be plus 6 decibels. If you put the right numbers in, the math works out to show this plus or minus. If d1 is 1/2 of d2, then we'll have 20 log of 1/2, and that will be the same as negative 20 log of 2, which will be negative 6 decibels. If we look at a graph of how the sound decreases as we move away from a point source, we see that it's a straight line in which every time we double the distance, which is plotted on the x-axis, the sound level decreases 6 decibels. Now, if we had the x-axis plotted as a ordinary arithmetic scale in which each segment was the same amount, rather than this logarithmic progression, the curve would be a smooth line leveling off to the right. By presenting it this way, you can see the 6 decibels per doubling of distance very easily. The rule for point source is about 6 decibels per doubling of distance, or to put it more mathematically, use of the inverse square law. It isn't true for all sources. Some things are more like a line. For example, a highway, a pipeline, something like that is generating noise all along a linear dimension. In this case, the loss is proportional to distance. So we can say the change in sound pressure level is 10 log of d1 over d2 instead of 20 log d1 over d2. And you can see this roughly from the sketch at the bottom where the line represents the noise source. If we go from position 1 to position 2, we approximately double the distance from the line directly in front of the position 1 or position 2. But if you think about how you're moving relative to the noise sources or the portion of the noise source out on the end, you can see that you haven't doubled the distance. It's only been changed a little bit if we were to draw a line from position 1 to the end and from position 2 to the end. Therefore, we can't use the inverse square law, and we have to use the simple distance proportional. So if we look at the chart on the right-hand side, if the distance doubles, the change in sound pressure level is 3 decibels rather than 6 for a point source. If it's 4 times as far or 4 times as close, the change is 6 decibels. 8 times is 9. 10 times the change is 10 decibels. 100 times the change is 20 decibels. Now this is all true only while relatively close to the line source, because eventually, as we move away from the line source, it becomes to approximate a point source. If you get far enough away from anything, it looks like a point. The rule of thumb is that while the distance is less than the length of the source, L, divided by approximately 3, then it's going to behave like a line source with loss proportional to distance. When you're beyond the critical point of L over 3, then it begins to act like a point source. Here's a graph of how the sound decreases for a line source. In this particular case, we're assuming a line source approximately 30 meters long, and the distance on the bottom is also in meters. And you'll also notice that the distance is arranged in a logarithmic fashion. That is to say, every unit doubles rather than just a fixed amount of increase per unit. So from 3 meters out to about 10 meters, there's a straight line of a small slope, and then at the point beyond 10 or 12 meters, the slope is greater. So in other words, we're seeing the line source 3 decibels per doubling of distance out to 1/3 the length of the line, and then it changes to point source 6 decibels per doubling of distance beyond that. Now, of course, in real life, the transition is gradual. There's not a sharp break, and I've tried to draw it without too much of a sharp break. But you get the idea. The sound decreases slowly at first, and then more rapidly. Most commonly, noise sources are either point or line, but occasionally we'll have something like an area source. An example of this would be the side of a building with noise sources inside, and the entire side of the building is radiating the noise that we're interested in. Now, if we assume this building has certain length L and a width W, with a width less than the length, there will be no loss of sound pressure level while we're relatively close to the source, and by that we mean the distance is less than W divided by 3, with W being the smaller dimension. Then, once we get beyond that point, the decrease in sound will be like a line source out to a distance of L over 3, where L is the longer dimension, the length of the building. And then beyond that point, it will behave like a point source. This isn't the sort of thing that one runs into too often, but I just wanted to be sure you realize that close to the side of a building radiating noise, as you move away, you can't expect much, if any, sound decrease until you get a significant distance away from the building, where it first acts like a line source and then a point source eventually. Plotting the sound decrease from an area source will give us something like this, where the sound level stays approximately constant out to the small dimension divided by 3, then acts like a line source out to the longer dimension divided by 3, and then like a point source. So we have 0 decibels per doubling, 3 decibels per doubling, and then 6 decibels per doubling of distance. Our discussion up to this point has been about point sources, line sources, and area sources in free field, that is to say, outdoors where there's no reflection of sound back. Indoors, the situation is greatly different and more complicated because of reflection of sound. We can't expect the continuous drop-off because we will have buildup of sound as we move away from the source due to reflection. You can see on this graph here, the blue line is the point source decrease line that we would expect in the free field. The red line is more what would be expected in an actual indoor environment, where the sound levels off as we get away from the source. When we're close to the source and the walls are relatively far away, the situation is like the free field. But as we move farther away, it becomes increasingly different. Calculation of where the change occurs and how different it is from point source has to deal with has to do with the properties of the room in terms of reflection and sound absorption, and will be covered later. When we look at how sound level changes with distance, there's no effective frequency. Geometrical spreading is the same for all frequencies, so the frequency content of the sound is unchanged. It's just the sound pressure level decreases as we move away from the source. However, there are other mechanisms which reduce the sound pressure level as well, and these differ depending on the frequency of the sound. Absorption by the atmosphere is frequency dependent, refraction by the atmosphere is frequency dependent, and so is interaction with barriers and structures. So this all becomes a bit more complicated than the simple geometrical spreading. When we want to consider how the sound level changes over large distances, we also have to look into atmospheric attenuation, by which is meant the transfer of energy from the sound wave to the air molecules, essentially heating of the air molecules. This is significant only for relatively large distances, usually greater than 100 meters or so. The variables that we have to consider are complicated in that it involves frequency, temperature, humidity, and distance. So it's not an easy calculation to make, and it's going to be continuously varying because the atmospheric variables are continuously varying. We just have to be aware that this takes place. Here's a table giving some idea of how we would calculate the attenuation of the sound. The three colored bands here are for three different temperatures, 30 degrees C, 20 degrees C, and 10 degrees C. And within each of these three, we have three values of the relative humidity. And then for each of the frequencies, we have different values of attenuation. And these are all in terms of decibels per 1,000 meters. So you see that it is rather complicated. One thing you can notice, though, easily from this graph is that the attenuation increases as frequency increases. For 125 Hertz, no matter what the temperature and humidity, the change is less than 1 decibel per 1,000 meters. So there's very little effect on the very low frequency sounds. Even at 250 Hertz, we're only talking a decibel or so per 1,000 meters. This is why foghorns, ship horns, that sort of thing, are low pitched, so that they will carry a long ways. On the other hand, if you look at the other side of the graph, 4,000 Hertz, you see that no matter what the temperature and humidity, again, there's a substantial loss of decibels per 1,000 meters, 20, 30, 40, 50, or even as much as 90 decibels. So high-frequency sounds will definitely not carry over great distances. In order to calculate how the A-weighted sound level will change with great distances, of course we have to consider all the octave bands and apply the correction as needed. Keep in mind, too, that the ordinary distance attenuation is still going on as well, the geometrical spreading for a point source. So this is on top of that. This is additional attenuation that has to be added in to go along with the distance attenuation as well. In addition to atmospheric attenuation by what we might call absorption, there's also refraction or bending of sound waves by the atmosphere. This can have the effect of greatly increasing or decreasing the sound level at a given point compared to what we would expect due to normal factors, geometric spreading, and molecular absorption. The refraction is affected both by the wind and also by the temperature profile. The neutral condition is one in which there is a moderate decrease of temperature as we increase in altitude. Under that situation, or with no wind, the sound waves travel in more or less a straight line. If there is an inversion in which the temperature increases as the atmospheric altitude increases, or if the sound is traveling in the same direction as the wind, sound waves are bent down toward the ground. And so at distant points where the sound wave might have passed over the head of people listening for it, it can be bent down, and so there can be an increase of sound compared to what would be predicted. In the third scenario, where the conditions are hot and sunny and there's greater than usual decrease of temperature with altitude, or if the sound is propagating against the wind direction, sound waves tend to be bent upward or refracted upward, and therefore at great distances there can be even less sound than would be expected from normal conditions. Since these things can be constantly changing, both the wind and the temperature profile, it makes prediction of sound at large distances, several thousand meters or more, pretty difficult to do. And the best we can do is come up with some sort of average with the realization that plus or minus 10 decibels or even more is quite possible depending on these other atmospheric variables. A further complication of sound propagation is the interaction with barriers, objects that may stop it from propagating. Some small part of the sound may penetrate through the barrier, but the more important factor is the sound that refracts over the top of the barrier. High frequencies tend to refract minimally, low frequencies tend to refract to a greater degree. This is all somewhat complicated and will be covered in more detail later. We also have to consider further sound interactions with objects such as indoor walls. There are three possibilities when the sound hits the wall. One is that it will be reflected, another is that it will be transmitted or go on through the wall to some degree, and thirdly that it will be absorbed into the wall in terms of change of sound energy into vibrational energy. This all merits a lot of study on its own, so I won't say any more about it here, other than to mention that it has to be kept in mind and appropriate calculations provided.